Okay, this is your assignment. One of the question from the assignment, right? Question number 4. So some students were struggling. So I thought maybe skip this question. So I'm going to go through this question. Please listen very carefully. You're going to get a mini project based on this question. So if you understand this, and then your mini project will be a breeze. What do you say? Okay, let's continue. So you guys see what's going on here. So you have a signal. You have a signal coming in. Okay, this signal is maybe an analog signal, continuous time signal, continuous time. It's coming in, and inside here, this box represents that it's getting sampled. After sampling, you get the discrete time sequence. Okay, after this sequence, you also can, the last time we called this also XPT, sampled signal, or here I'm going to call this same thing, X subscript P as a function of T, X subscript S as a function of T. Right, so after going through the sampling, so you're going to get some sequence, something like this. Then after you go through the sample, ideal construction, let's say you go through low pass filter with the bandwidth, the output will be, you get the output. Maybe after sampling, after filtering, you might only get 2 out, discrete. It's a discrete signal. YT is the continuous time signal. If you are able to recover your input, if the same input comes out at an output, the input and the output the same, then you have done a successful sampling and reconstruction. Okay. Remember we learned from the last time, if your sampling rate is more than twice the, I can use omegas of S or Fs of S. If the sampling rate is more than twice the signal bandwidth, then you will get a original signal without aliasing. So if you haven't gone through the previous nodes, maybe you'll be still confused. If you've gone through the previous nodes, then you wouldn't be confused now. So in this problem, so this is the filter. So in the part A, this part. So the input signal is 1 plus cosine. The input signal is 1 plus cosine 15t. Okay. At the sampling interval or the sampling time, every 0.1 second it's sampled. Every 0.1 second it's sampled, you know. So like from year to year. So that's it's too small. Okay, it's understood. So now you are told to find a YT. To be able to find YT, you should be able to draw first. Okay. So we already used, you know how to do this from the previous lecture. So let's do this again. Any questions so far?
No, sir.
Okay. How about any other students? Please, if any doubt at all, please ask me, because it's going to be a mini, you're going to have a mini project based on this. It's going to be a very simple mini project, and you have to do a MATLAB simulation. Usually the students have struggled with mini projects in this class, but this time, due to the lockdown, I'm giving a much easier mini project, which can be done in a couple of days. Okay, recall from the last time, there was signal coming in. Okay, this is the input signal. It can be a continuous time signal. I just drawing this to show that it's continuous time. Then you have a sampler. Series of impulses, right? Remember? Samplers, PT. And the output is going to be the sampled signal. X, a function of, I'm going to call this, the last time we called this XPT, and they're the same thing. Sampled output. Sampler. Okay, is this clear so far? The last time we already been through this configuration. Signal comes in, it gets sampled. So the output is going to be a sampled output. So depending on your sampling frequency, you will know whether it's going to be getting aliased or not. So you only can find that out by drawing it. But after the sampling, if you want to recover the signal, as you know, the sampled signal usually get replicated, right? Replicated at different frequencies. So you want to filter what you need. In this case, we are using ideal reconstruction of the original signal. It's a filter. I just call this filter, which is the ideal LPF, low pass filter. After filtering, you can get back your original signal. Should be able to get back if you have done the correct, you have done it correctly with the proper sampling frequency. So you don't have to know too much in this problem. So you know from the last time, the Fourier transform of sampled signal so you know, right, from the last time, the Fourier transform of sampled signal. So this is something that you want to remember. is 1 over the sampling interval, summation of negative infinity to positive infinity, x omega minus k omega sub s. So this is the only formula that you need to draw. To draw, you cannot simply draw. You need to use this formula to figure out the replication, at what frequency is getting replicated, and how much it is scaled up or down. Okay, now you're given that your input signal 1 plus cosine 15 pi t. T is equals to the sampling interval. When you are given time is understood, this is a sampling interval. So now you're supposed to draw x, the Fourier transform of the sampled signal. Where the sampled signal is the input signal multiplied by the sampler, the impulse. After you draw this, then, so first thing you have to draw this. Next, you have to determine the expression for yt. Expression for yt. So again, let me refresh. This is the sampling interval. Okay, please mute everyone. Mute the mic, please. Sampling interval, sampling frequency, sampling frequency, so the input signal, let me take it out here. The input signal. It has a DC and then an AC. Okay, to be able to solve this problem, we have to convert the input signal. We have to transform the input signal, which is given in time domain, to frequency domain. So what do you do when you want to transform the time domain signal to frequency domain? What do you do? G?
Yes, sir.
What do you do when you want to transform the time domain signal to frequency domain?
Check the disease, sir.
Kavin?
Fourier transform, sir.
Okay, very good. Fourier transform. I don't know what you're doing there, G. Are you talking to somebody on the phone?
No,
Okay.
sir.
Okay, Fourier transform. So we have DC here, DC part. The Fourier transform of it's 1, right? DC is 1. So what will be the Fourier transform of 1? So we have table here. Okay, so you can see the Fourier transform of a DC is 2 pi delta as a function of omega. 2 pi delta as a function of omega. So do you know what this guys this means? You means we have a delta function with the amplitude 2 pi, sorry, amplitude 2 pi, and it's located at omega is 0. Is this news to you, or you guys know? Because we have done all these things in mathematics 2A, I believe. A lot of things we have already done in mathematics 2A. So here we are just applying it. So similarly, the Fourier transform of the AC signal, in this case is cosine, say cosine omega naught t. Fourier transform, if you look at this signal in the frequency domain, what will happen is, okay, let me write the equation first. It's going to be pi delta minus omega naught plus delta omega plus omega naught. You can find this information in the table here, right here. The Fourier transform. So this signal, there's no bandwidth for this signal. It's only a single frequency. Okay, it's a single frequency. A single frequency. For this signal, you have a spike here at pi. Then you have another spike here at pi. In the middle is 0, omega 0. So at omega equals to omega naught, you have 1 delta with the amplitude pi. And omega is minus omega naught. You have another delta function with an amplitude pi. Is that clear, guys?
Yes.
So please understand, in the last time, the Fourier transform was given to us. This time it was not given to us. If you remember, if you did the last week, the Fourier transform of the input signal was given, right? But now it's not given to us. That's why we have to do the Fourier transform. In order to be able to do this problem, you have to do the Fourier transform of the given signal. After taking the Fourier transform, now you combine, what will be the Fourier transform of this function then? What will be the Fourier transform of cosine omega naught t? So what do? You just combine these two. You just combine these two. Graphically, DC is 2 pi, so it's going to be taller. So the other guys, pi, one is located at minus omega naught. The other one is omega naught. So you know from here our omega naught is 15 pi. Okay, so you're going to replace that with 15 pi. So that's a Fourier transform of the input signal input. Any question on that? Any question?
No.
Okay. So let's say if this is what I'm just giving you the physical idea visually. So signal coming in. If you look at this from the frequency domain point of view, and then it's going to be sampled with the sampling frequency is 2 pi over t, which is 2 pi over 0.1, right? So omegas of s is 20 pi radians per second. So it's going to be sampled at this frequency. What does this sampling means? After the sampling, what's going to happen is the input signal is going to be copied and pasted at the sampling frequency. It's going to be scaled, and then according to the formula that we had, it's going to be scaled. So like the output is, so we had this formula here, remember, for this output. It's 1 over t. I'm rewriting this formula again. So t 1 over 0.1 . What was omegas of s? 20 pi. So that's the equation that you need to be able to plot this. So what this formula is going to do, what this equation is going to do, it's going to scale it. 1 over 0.1 is 10. Scale the input signal And then it's going to place the signal when k is equal to 0. It's going to place a copy there. It's going to copy it there. And then when k is plus minus 1, it's going to have the original copy plus this copy. Plus minus 1. Okay, let's do it in detail and see. Any questions so far? Any question?
No, sir.
Okay. So when k is equal to 0, so I'm going to put this in different colors. Maybe you can see when k is equal to 0, x as omega is equal to 10. So what this means, you're going to have a signal. The original signal is centered at 0. So that's a signal when k equal to 0. The original signal is now scaled. Okay, next, use the dummy colors. Okay. So now when k is equals to plus minus 1, so now what's going to happen is the signal so this signal, in addition to this, at k is equal to 0, it is also going to appear at, okay, right here is 0, right? 0, right here is 0, 5, 10, 15, 20. Okay, let me put this in green. So each division here, it's 5 pi per division, like each division. So this signal, it's also going to be replicated at minus 20 pi. I'm going to delete these things, so because it's understood the shorter one is 10 pi, the taller one is 20 pi, because they will clutter the drawing as you move along. So at k equals to plus minus 1, you're going to get this plus this. I'm just drawing them on a different scale. I mean, on the separate drawings. But actually, they all appear on they all added together. At k equals to plus minus 1, they all added together. We put them together later. For now, I'm just drawing them separately. So next, when k is plus minus 2, when k is plus minus 2, so the equation is going to be x as omega is equals to 10 plus minus 40 pi. So the 40 pi is referring to the frequency where it's going to be replicated to. So let me just copy this. I mean, just draw. So, okay, 40 pi is like this is 20 is 40. It's minus 20 minus 40 pi is 0. So at k plus minus 2, what's going to happen is, let me put them all together here. At k plus minus 2, so I'm just drawing this only for up to k plus minus 2. So I'm going to just move them all on a single graph. Okay, hold on, please. There's a mistake here. Okay, there's a mistake here. I need to fix it. Maybe I didn't. Earlier on, I said this is going to be. So I'm going to move this over here because earlier on, I said it's going to be 5 pi per division, right? So I said this is going to be 5 pi per division. So this is 5, 10, 15, okay? Minus 5, minus 10, 15. So in that case, every one of these has to be moved this way. So that's why you have to scale it properly. Otherwise, you won't get, when you put them all together, you will get overlappings, which will be misleading. Okay, this is more correct because I'm using, just to tell you if you are confused. So like this is 5, this is 5 pi and 10 pi. So one division is 5 pi. Okay, that's all the mistake I made earlier. I didn't, I'm supposed to have it to scale. Sorry about the confusion. So any question until now, before I put them together?
No, sir.
Okay, this was when a k is equal to 0, you know, this was when k equal to 0. Now when k is plus minus 1, you bring it to minus 20 pi somewhere here. Okay, so it's going to be like this. This is going to be for k is plus minus 1. General put black in color. So this is for k is plus minus 1. I'm just deleting some of this because it's cluttering the drawing. It's understood the shorter one is 10 pi, the taller one is 20 pi, and each division is 5 pi. In this case, you can see the frequency here is 20 pi minus 20 pi. I really don't worry about as long as they are on scale, you don't have to worry about putting numbers there because we're going to filter out all of them later. So now when k is plus minus 2, this will be, the one in purple will be added to. Just copy and then copy and then paste. So this is how it looks when k is plus minus 2. previously I was not very clear enough on this. This is when k is plus minus 2. So as you move on, the pattern will be repeated, the pattern will be repeated. As you move on, there will be more, there will be 1 year, okay, and then there'll be 1 year and so on. But this is sufficient. Okay, plus minus 2, you shouldn't be drawing anything extra. But it goes on, it usually it goes on, but you don't have to put so many because you're going to filter it out. Any question on this drawing?
No, sir.
Okay, guys, good. So now you want to filter cutoff frequency. Zero minus 1/2 sampling frequency plus 1/2 sampling frequency. And also it was given that the filter amplitude is 0.1. It was just mentioned. If you go to the question here, so it's mentioned here, the filter amplitude is T. T is 0.1. So now you're going to take this filter, one half the sampling frequency, 1/2, what was the sampling frequency again? 20 pi, right? What was the sampling frequency? 1/2 20 pi. 1/2. So that's going to be minus 10 pi plus 10 pi. That's a cutoff frequency. That is the cutoff frequency of the filter. So 10 pi, this is 5. So 10 pi is here, minus 10 pi. And then plus 10 pi is here. So you just go ahead and put the filter. It doesn't matter, it doesn't have to be to scale. It's on a different scale. So long you just mentioned is 0. As long as you mentioned its amplitude is 0.1. Maybe I should put this 20 pi. Just to show you that it's filtering everything in this bandwidth, plus minus 10 pi. So this is the filter. After filtering, Okay. So you get the signal 20 pi. After scaling, we can look here, the filter. So we look, the filter is 0.1 amplitude. And this is 20 pi. 20 pi times by 0.1. So let me put this bigger. 0.1 is a filter amplitude. So now when you filter is going to attenuate the signal to 0.1 scale. So 0.1 times 20 pi becomes 2 pi, 0.1 times 10 pi becomes pi. So this is what being filtered out. And that's going to be, the frequency of location is minus, 5 pi. Minus 5 pi. Correct? Frequency of location. So this is the output. Inverse Fourier transform of the output is yt. Yt is equals to what? If I do the inverse Fourier transform of this signals here, you have a DC with an amplitude 2 pi, and you have a AC with an amplitude pi located at frequency 5 pi. So how would you do the inverse Fourier transform of this? Zifeng?
Yes, sir.
So what is the inverse Fourier transform of 2 pi? So this is, okay, if you want to write this in, so 2 pi, this is omega 0, 2 pi. So omega pi omega plus 5 pi Okay, so now if I want to, so this is your output in frequency domain. So if I want to do the inverse Fourier transform, yt is equals to what? What about Yenle?
Yes, sir.
So what is the inverse Fourier transform of this 2 pi delta omega? Just now we had a table, isn't it? From this table, we know the inverse Fourier transform is 1, isn't it? Right? Yenle?
Yeah, yes, sir.
And then plus the inverse Fourier transform of this part is how much? What is it? The inverse Fourier transform of this. Go back and look at the table and tell me, Jintek.
Cos omega naught t.
So in this case, what is omega naught? Cos.
5
Sorry,
pi.
cos. Okay, very good. Now, Jintek, you know everything, and I ask you a question, but in the exam, something is going on. So this is the output. This is the output. But what was our input? What was the input? 1 plus cosine 15 pi t. This was the input, right? Guys,
Yes. Yes.
is the input same as output?
No.
Yes. Why is it no? Because we already lost the frequency. It was 15 pi, now it's already, output is coming at 5 pi. So we have lost the signal. We have lost the signal. YT, this is a filter. When you recover the signal, they should be the same, but they are not the same. Therefore, we have lost the signal. Therefore, I can say aliasing has occurred. Why aliasing happens? Because our sampling frequency must be at least 2 times the highest frequency. The highest frequency was 15 pi, right? Cosine 15 times 2 must be 30 pi, but our sampling frequency was only 20 pi. We have lost the original signal. Is there any question on this?
No.
What about the other guys?
No, sir.
No, sir.
Okay, for assignment 2, since I already done this for you, right? I've done this for you. For assignment 2, JJ, unfortunately, you have to end in the assignment 2 again. Is it okay, JJ? JJ?
Yes, sir. Yes, sir. Can, sure.
Assignment 2, since I already done, show you guys how to do. For assignment 2, this was question number 4, right?
Yes.
Question number 4. For question number 4, you repeat the above for omegas of S, sampling frequency is 40 pi. So now you repeat. Now you see a sampling frequency is greater than 2 times the signal frequency, the input frequency, omega naught. Okay, so now you go ahead and go through the same process, and then you come to a conclusion. You must verify whether the input and output is the same. If the input is same as the output, then there's no aliasing, and therefore we would have recovered the original signal. Understand, guys? All of you?
Yes.
Yes, sir.
It's better, right? Then now actually it's kind of easy. You just use the same problem here. You start with the same problem, then you change numbers. You change numbers and then keep drawing and changing here and there, and then you'll arrive at the answer pretty soon. Okay, guys, you can have a few minutes break. I'm going to be back in 5 minutes, but I'm sitting here. I'm not going anywhere. But I'll show you for mini project what you need to do. Maybe not now, maybe later. Do you guys want the break or not? If I no break, we can finish quickly.
Carry on, sir.
Okay, carry on. Just one more quick one. So this question here, we have already done. Then I gave you an assignment. This is done. Now you look at this. The same kind of problem. The input, okay, same problem here, same as this. Okay, yeah. So there's no filtering required. Just going to do this part here. So try to understand these problems. Your mini project will be very simple based on these problems. So in the problem, the part B, in part B, what you have is in part B, our input signal is already given as a Fourier transform in frequency domain. Is 1 over 1 plus j omega plus 1 or 1 plus j omega, the same thing. And the sampling interval, the sampling time is 1. So sampling interval is 1. So omegas of s is 2 pi. And then we are also given the input. So you need to find the magnitude. Magnitude, remember last time we did this, right or not? The magnitude is square root of 1 plus omega squared in the previous lecture. And then I also showed you how to sketch this, remember? If you sketch this, we also showed you how to sketch this. You can sketch either going point by point. All you need is 3 points, I said. Minus 1, 0, 1. X omega. When omega is minus 1, because you have a square function, because of this square here, this function will never go to 0, right? Even if you put a plus or minus 1, it will be squared and you're going to get 1. A plus or minus any number. So whatever inside the square root is never going to be negative. And the function, the amplitude itself is never going to be negative. When you put minus 1, you get 1 over square root of 2. When you put 0, you get 1. when you put, so this is also 1 over square. So these are the 3 points required to be able to draw this. This problem, they give you the equation. So if you draw, when omega is 0, let's say you have 1 right here. One. When omega is -1, let's say it's plus -1 is here. It's 1 over square root of 2 is somewhere here. So if you continue to sketch this, this is going to be like this. It's going to be like this. Maybe I should sketch it in a more elaborate manner so that you can understand the nature of this signal. I'm going to draw it really big. So let's say if you sketch, this is what is going to happen. Roughly, if you can try, it's going to do this. Okay, it's going to do this, something like this. So please note that this function is never going to be 0. See, it's not going to cross. It's never going to be 0. This is 0. Crossing means it's already 0. So it's never going to cross. So there's going to be always an amplitude, even when the omega gets very big. So therefore, this signal is not band limited. The last time, remember, when the previous examples, we had a band limited signal. When you have a signal like this, when you have a signal like this, then it's band limited. Let's say in this case, remember the previous example, we had something like minus 20 pi or anything like this. So it's band limited. You can see after the 20 pi, the signal is 0. So it's well-defined signal. That's band limited. So for example, this is band limited. Limit. This is not band limited. Not band limited. If that is the case, let's say we bring this signal here. This is a signal. If you bring it, so if we bring this signal, so we bring the signal and we sample it, and the sample output one over t is 1. not coming out right. Okay. Okay, let's say this is the signal centered at omega is equal to 0. Okay, at k, let's say for example, when k is 1, then you're going to get another signal here centered at plus minus 2 pi, for example. When k is plus minus 2, you're going to get another signal here. When k is equal to 3, you're going to get another signal here. When k is 3, sorry, is 6, right? So this is up to k is equal to plus minus 3. So what's going to happen is you're going to have a lot of signals. What I'm going to do, I'm going to copy this over. So you're going to have one signal here. Then you have another signal here. Okay, so this is what's going to happen. So the net result is going to be something like this. Because if you see in this region here, you look at this region, because this is not a band limited signal. So one signal is overlapping the other signal. It's not band limited. You cannot avoid this, even though if you're going to sample at Nyquist frequency and above. It's always going to be aliasing. If I happen to draw this signal, it's going to be something like this. It's going to be something like this. Even when you use a filter to filter it out, you're not able to recover the original signal. Okay, you won't be able to recover the original signal because the signal is not band limited. There's always going to be overlap with the adjacent signals, which is going to distort the original signal. So that's the answer for the, that's the answer for part B. So now let me ask you, does aliasing occur in this case? Does aliasing occur? How about JJ? Does aliasing occur?
Yes, sir.
Yes, aliasing occurs.